In this presentation, you'll learn about Talking Technicians, MNTEC's podcast. I'm Peter Kazarnoff, faculty at Portland Community College and co-PI of MNTEC. You can get in touch with me by emailing me at peter.kazarnoff@pcc.edu. The three takeaways from this presentation is that MNTEC has a podcast about micro-nano technicians. The second takeaway is that podcasts can be used as curriculum and be used in your classroom. And the third takeaway is that you can contribute to the podcast by suggesting a guest. The Talking Technicians podcast is available on all major podcast platforms. Search for Talking Technicians in Apple Podcasts, Google Podcasts, or Spotify. You can also listen to the Talking Technicians podcast on MNTEC's website. Go to micronanotechnicianeducation.org, click the Students and Parents link, and then click Podcast. All of the episodes that have been posted so far are available for you to listen to. If you know any technicians that would make great guests for the Talking Technicians podcast, please send me an email. I'm always looking out for great guests to share more stories with you.
Hello, my name is Kenny Moses and I am the Chair of Engineering and Technology at Southern University at Shreveport. This is a brief presentation about the 2+2+2 matriculation model in STEM. Southern University at Shreveport is a two-year community college arm of the Southern University HBCU system. Southern University's student population is consistently 90% minority and more than 70% female. Students under the age of 24 make up about 51% of the student population. In the Engineering and Technology department, we have an Associate of Applied Science and Engineering Technology with concentrations in Electrical and Computer Engineering Technology, Process and Petroleum Engineering Technology, and Industrial Engineering Technology. We also have Certificates of Technical Studies in Engineering, Electrical Power Line Technician, Petroleum Technology Operator, among others. The purpose of the 2+2+2 model is to increase early engagement of students in high school, which can decrease the number of academically underprepared students entering college. It's to expand post-secondary educational opportunities to improve student outcomes, and to increase enrollment, persistence, and graduation of underserved populations. The first two in the model is set up to provide students the opportunity to earn a CTS in engineering while in high school. It's about 23 hours. The second two provides direct transfer of the earned CTS into the Associate of Applied Science and Engineering Technology degree. The third two represents either employment with an employer partner or transferring to a four-year partner institution upon graduation. This is a brief overview of Southern University's 2+2+2 matriculation model. See you soon.
Hi, I'm Tanya Fultons with the Network for Computational Nanotechnology at Purdue University. You may know us as the group that hosts NanoHub. I invite you to come see our high-tech presentation, NanoHub's Open Access Cloud Computing Resources for Nanomanufacturing, Nanobio, and Data Science later this week. Here's the quick Lightning overview. I'll say a little bit about undergraduate research opportunities that will become available with the NCN nodes via MNTeSIG. I'll give examples of some new NanoHub resources that may interest you if you'd like to introduce your students to coding in Jupyter Notebooks, to data science tools and biological simulations. And I'll provide a way to request more information and free training. Here's a quick view of some of the biological simulations. In this simulation, you can see a green macrophage hunting a blue bacterium through a maze. What's important to note is that in all of the simulations, there are parameters that students can change that affect the behavior of the cells and tissues involved. In this next simulation, students can design new nanoparticle-based nanotherapies and explore how these therapies interact with the cancer cells. This simulation shows the interactions of three different types of cells. The large green mass is made of cancer cells. You can see red worker cells actively transporting the therapeutic agent, the blue cargo cells, to the cancer cells. The red worker cells then return to pick up new cargo cells to continue the therapy. I hope that some of these simulations have sparked your interest and that you'll come and see the full presentation later this week.
Hello everyone. I'm going to talk a little bit about what you can expect to see in the longer presentation entitled Hands-on Professional Development at UNM with your students. And I'm Matthias Plyle. I'm the PI for the Sports Center for Microsystems Education. The SCME has been providing professional development in micro-nanotechnology for over a decade. So consider joining us at the University of New Mexico's MNTeSIG clean room for a full week or two of intensive hands-on experience doing microsystems fabrication. We encourage you to bring your students as well. There are stipends available to support this endeavor. So the URE project, which stands for Undergraduate Research Experience Project, is a supplemental award to our Support Center for Microsystems Education grant. The idea there is to bring faculty in for professional development with their technology students. So this is a new opportunity. The SCME URE Undergraduate Research Experience is targeting community college technician students and their instructors. It's open to all tech faculty and students. So the faculty get a stipend under the SCME grant, and the technician students get a stipend under the URE supplemental grant that we received this last year. There are lots of topics you can endeavor to research while you're here. There are fabrication processes you'll learn about, characterization methods. You can research MEMS design principles, applications of MEMS devices and microsystems devices. Dr. Jackson helps us with these experiences and leads us with the microfluidics and microneedles processing and flexible electronics. And there's some modeling you can do online as well. We do have access to certain modeling software. And we have metrology tools, including a scanning electron microscope, thin film measurement tools. Also, when you come here to UNM, you get to interact with a couple of our grad students, PhD students, as well as Dr. Jackson, who's a long-term expert in biomems applications and fabrication. So you get to work shoulder to shoulder with these folks. So the presentation, the longer presentation, will cover all of these things in more detail, who the SCME is and what we do, for those of you who don't know us yet. A little bit more about the URE opportunity. What we've done this year, we've had 3 groups in this year, and what our plans are next year. And also projects and topics to explore in more depth. And then how you can get involved with us. So we're looking forward to seeing some of you at our hands-on opportunities next year. And I also want to pitch the High Tech Conference. If you haven't signed up for it yet, please do so. It's going to be on Wednesday and Thursday of this week. So right after our Monday-Tuesday conference. It's also online. It's free if you use the SCME code. So if that code doesn't work, then you can use the NACK mode, the NAC code. And these are free if you use the codes. And then watch the presentation by Jared and myself and 3 of our URE students that we've submitted to the High Tech Conference. You can also view that same presentation on our YouTube site, and I'll have the slide deck available for you so you can open up the slide deck and be able to click on these links. And there is also a keynote by Jessica Gomez during High Tech. She's a micro-nano technician who worked her way up to becoming the CEO of Rogue Valley Micro Devices. In fact, she founded that company. So that's a really good keynote. I encourage you to watch it. For those of you who attended MNTeSIG last year, she gave our keynote last year as well. But this will be new. And last but not least, I want to see all of you at the virtual poster session. So you can check out the poster page on the MNTeSIG website underneath the MNTeSIG Live drop-down menu, and it will tell you more about how to put this software on your computer if you haven't done so already, and how to enter the virtual poster session. So we have room for about 50 people, so if you can't get in, just wait a while and then you can try again. So that's my avatar, so you'll be able to find me at the virtual conference. So I'm looking forward to seeing you all, and I hope you enjoy the rest of the day.
While gold nanoparticles are commonly used in nanotherapies because of their beneficial properties, such as having a high surface area to volume ratio, along with having a stable and non-toxic nature, in addition to many other qualities, gold nanoparticles do not carry antibacterial properties that are important to combat the interactions between bacteria and cancer cells. However, silver nanoparticles possesses properties that the gold nanoparticles lack, such as antibacterial, antiviral, antifungal, and anti-cancer qualities. But it is toxic to the human body when silver nanoparticles are used by themselves. With this study, we look to create gold-silver nanoparticle hybrids where a silver nanoparticle core is wrapped in gold nanoparticles while conjugated to cancer-specific antibodies in order to enhance the best properties of both the gold and silver nanoparticles. This project focuses on covalent and passive non-covalent conjugation methods in order to conjugate, optimize, and link the silver nanoparticle core to cancer-specific antibodies. A variety of purification, characterization, and proof of efficacy methods will then follow to confirm the success of conjugation. Entering the next step of the project, the energy transfer of the nanoparticle hybrid to antibodies will be analyzed through femtosecond laser pump probe, spectroscopy, and microscopy techniques.
Hello and welcome to my brief presentation on the feasibility of an OAI mask aligner at Rio Salado College. My name is Wesley McKeever. Let us begin. In 2018, Rio Salado purchased a mask aligner, and it has sat unused ever since. It was not very well understood on how to facilitate this equipment, and it had never even been plugged in until I got my hands on it. With the support of the University of New Mexico, as well as OAI, the manufacturer, I was able to explore the feasibility of a mask aligner on the Rio Salado campus. After many hours of research, I was able to identify the limiting factors to the equipment installation. These limitations could cost as low as $1,000, way below initial expectations. Further into the research, I can conclude whether Rio Salado can use this equipment in its curriculum. Additionally, I identified some opportunities for future research by looking into adding the chemistry process capabilities. Check out my poster for all the details. Thank you for your time.
In order to best prepare for the CCIC Innovation Challenge in a virtual world, we first identified a global phenomenon that devastates a large number of people, in our case, breast cancer. There are 300,000 new cases of breast cancer each year, contributing to the 4 million cases in the US. We then looked further into the current treatment options and how available, feasible, and effective they were for the general public. We looked at chemotherapy, current nano-based drugs, such as Abraxane, as well as surgery options and other drugs to combat cancer. Because of the limitations of current drugs and options, a novel drug called the nanobio MAB, which has antibacterial, phototherapeutic, and antibodies attached through conjugation techniques, was developed as a more efficient, lower cost, and more available product and treatment to the general public compared to current cancer treatments and drugs on the current market. We considered the possible side effects of the drug, whether it was a better alternative compared to other cancer treatments, feasibility, and whether it was cost-effective and can be mass-produced in the future with the help of industry professionals. To further support our theories, we performed nanoparticle and antibody conjugation techniques, as well as phototherapy studies. After considering all these factors, we were able to better prepare for the CCIC Innovation Challenge, even through a virtual world.
Greetings and welcome to our presentation preview about using photonics to determine the wavelength of red light. My name is Greg Kepner and I am serving as the co-PI of the Micro Nanotechnology Education Center. My colleague and subject matter expert, Professor Frank Reed, and I will be sharing this presentation and lab demonstration with you. We will share the objectives of the demonstration, some theory and concepts to help you understand the demonstration, a description of some lab equipment and how it is set up, the procedure, as well as measurements, calculations, and a comparison of the lab results to the actual wavelength. For the demonstration, we will use an Impact Photonics kit. We will go through the procedure and identify all of the equipment and components needed to perform the laboratory activity. In the demonstration, we start by setting up the lab equipment to allow laser light to pass through a diffraction grating that has 1,000 slits per millimeter. When light is passed through a diffraction grating, interference patterns are generated which result in bright modes and dim areas formed by the interaction of the light waves from each slit. This picture shows the laboratory setup, including the laser, diffraction grating, and the white beam block target, which blocks the light from passing and serves as an easy way to mark the location of the spots where the bright modes contact the target. This picture shows the path of red laser light with red arrows as it travels from the laser through the diffraction grating on its way to the target. The bright modes M-1, M0, and M+1 are the points of contact of the laser light on the target. In this view from above, the target and diffraction grating are shown and should be parallel to one another, and the laser, to the right, not shown here, should be perpendicular to them. In this picture, the red lines show the path of the laser light through the diffraction grating and to the target. For perspective, the bright modes are also shown. Notice how two right triangles are formed by the laser light paths in the plane of the target. The angle theta can be calculated using a trigonometric formula once the distances x and l are measured. Using this information, the wavelength of the light can also be calculated. Please join us for our complete presentation of using photonics to determine the wavelength of red light.
Hi, I'm Deb Newberry, and I'd like to invite you to listen to my presentation titled Nanotechnology and Agriculture, a unique and positive combination. I've been doing nanotechnology for over 40 years, so for quite a while, and originally nanotechnology was viewed as a very particular discipline that required expensive equipment and laboratories. And then it evolved into the impact that nanotechnology could have on the semiconductor fabrication industry, as we kept trying to put more and more transistors, more and more computing capability into smaller and smaller surface areas. So semiconductor manufacturing was perhaps the first industry that really took hold of nanotechnology. More recently, it's evolved into the medical arena. Nanoparticles that can detect and treat tumor cells. Nanotechnology was also very involved in some of the treatments that we've experienced with regard to the recent pandemic. A lot of times we don't think of agriculture as something that would involve nanotechnology. When we think of agriculture, we probably think of fields of corn and wheat and combines and a lot of dirt and dust and gritty farmers, perhaps. My dad was a farmer, so I know it's okay if I say that. But agriculture has been substantially and significantly impacted by some of the developments that have come about in nanotechnology. Everything from coating the machine parts to make them last longer, to producing sensor systems that we can put into the soil in the fields that can measure the moisture content so we can figure out which parts of the field need the water, which parts of different fields don't. Vineyard owners in Australia were one of the first first folks to use this type of sensor technology. By putting these sensors around their vineyard, they knew exactly where the grapevines needed the water and those that didn't. Now, nanotechnology is also impacting sensing right on the leaves of plants. We can create nanotechnology sprays that will rest on the leaves of the plants. And as they do so, they can detect different insects or fungus that might be infecting the plant or impacting the plant. And a lot of times it's not just one field, or you want to catch those infestations very early. By using a nanotechnology related sensing system, you can find the parts of the field where that infestation is starting, take care of it, nip it in the bud, so to speak, before it spreads to the whole field. Again, reducing the cost, reducing the time, increasing the yield, protecting the crops. We can also create crops that are resistant to high temperatures, a lot of water or very little water, cold temperatures, by the use of nano-enabled technologies. One of the things that for me is the most exciting is we're using nanoparticles to fertilize the plants. And these nanoparticles are much more efficient, use much less nitrogen, so we don't have the nitride runoff that is the bane of a lot of large crop fields where we fertilize the plants. Not all the fertilizer gets absorbed or used by the plants or absorbed into the soil, and it ends up flowing into the streams and the rivers, the water supplies that surround the fields. And with nanotechnology, we can create fertilizers that don't have that particular element in them that causes the toxicity to occur in the water systems. So there's lots of applications that are coming about because of research in nanotechnology specifically geared towards the agricultural arena. I'd like to invite you to join me as I present the research, the applications, some of the things we need to consider, and talk about the multiple disciplines required to take technology, nanotechnology from the research lab into the cornfields of the United States and the world around us. Thank you. Hope to see you there.
Hello, this is Oscar from Penn State NAC, and I'll talk about effective ways to teach all the way from quantum mechanics to solar cells. This work is being done in collaboration with Erin Cholak from Ankara University and Osama Abdul-Karim from Penn State. Unfortunately, quantum mechanics seems to be a very dreadful course for many, and we build unintentional barriers for ourselves. However, quantum mechanics at the same time offers a great wealth of information and understanding physics of semiconductors. I'll first start by introducing PhET, University of Boulder's Colorado Boulder's webpage, and you can download many simulation tools and play with them with your students. Now let's look at a couple of them, like blackbody radiation and Rutherford scattering. I just downloaded them to my computer. And if we send, like in the case of Rutherford scattering, these alpha particles, we see that the atoms actually scatter these alpha particles. And blackbody radiation, so if we play with the temperature of the emitter, like in case of sun, we see that the radiation pattern change because we are getting a different wavelength. Yes, there are so many other simulation tools that you can work with, but then the essential question still lies there. Where does this band gap come from? As in the case of semiconductors, there is a forbidden zone where the electrons cannot propagate or cannot reside within this crystal of silicon. So for that reason, we've written this we're still working on the standalone MATLAB package. We've written these codes, MATLAB codes available, and we're offering for them to you. And then I'll talk heavily on that in my talk, my longer talk. So in the case of an electron that is a wave, actually, how does it actually interact with these kind of potentials, like these kind of tunneling through barriers or hopping over these wells? Now let's look at a couple of them. The student just runs the simulation tool, and depending on the parameter that has been entered, the student examines the result, like the transmission through a barrier, and understands wealth of information. Or the student again enters a parameter, and based on that, now for example, the student will try to see how the waves propagate through these barriers. We have a barrier here, and then the wave package travels to the other side. Or we might have a finite well, or we might just be going through a single delta potential, like a very tiny little delta potential, as in the case of this. So let's look at that. Like this kind of a marathon runner electron can be just propagating through that. How about if we just put two of these together? If we put two of them together, we see that we're starting to open up some forbidden zones. And if we put even more, like n of these together, and like 30 of them together, we start to see the opening of these forbidden zones where the transmission is completely forbidden. Now I'll just jump to the conclusion and show you what would happen if we had a perfect periodic array of these. A lot of these potentials together, cascaded together, what would happen? I'll just run and pause the video as the simulations take a little longer. But as you can see here, there are some opening of these forbidden zones, even in the case of the simplistic one-dimensional picture. So the students appreciate and start to understand where these band gaps might be coming from. And you might ask now, how am I going to connect to the diodes and solar cells? I'll talk more about it in my longer talk, but we have great solvers on NanoHub, and I've been very successful in conveying that information to my students thanks to the PN Junction Lab and the ADAPT 2.1 solar cell simulator. So I'm going to be talking more about them in my longer talk, but I'm utilizing NanoHub simulation tools as well. All right, thank you. See you in my longer talk. Hi, this is Özgür from Penn State, and I'll be talking about atomic force microscope and how to teach them interactively, especially during the COVID times. So this is a famous video on atomic force microscopes. I'm sure a lot of you have already seen it, but we have a laser at the top of a sharp tip, and then we're hovering on top of the surface and gathering information about the patterns as we're going up and down on the patterns. Like you can see, the laser point will be shifting, and then the whole thing will be deflecting, and that will be important information for us. In my bigger talk, I'll be showing you like these kind of simple apps and also more complicated things as well for our students, for their better understanding, like how we can increase the sample height and apparently the set point, and then how we can also incorporate the gain as much as we want so that we can now latch onto the surface with the help of the feedback loop. And also let's look at a couple of more things like the van der Waals forces, essential things when we talk about atomic force microscopes, like where are we, how like things are attracting each other, and then how things are starting to repel each other by giving us infinite energy to get them together, right? And I'll be also talking about this wonderful simulator, SPM simulator by Microscope, and a training tool essentially. Then you can have all the like laser alignment and everything, even get a scan. And at the later part of my talk, I'll be talking about the NanoHub's VEDA simulation tool, which is a beautiful simulation tool at the research level. And just to show you what we can do with this, for example, this thing is now showing us how we approach to the surface. And this is, as you can see, the deflection that we will get from the tip. So there's zero deflection while we're approaching, and in the blue line. And then all of a sudden we snap down to the surface, and then we deflect in the positive sense because we are starting to go into the sample. We're indenting into the sample. And this is also showing us how we remove the tip from the surface too, like both coming and approaching and retracting. So we can also see like differences, like in terms of the indentation, for example, like this is indenting like a 1 nanometer on the surface on this harder surface, which is 1 gigapascals. But if you switch to like a soft surface, 0.1, you indent more. Like students understand, like we can get information about the surface, but we can also get a scan on the surface too. Like this kind of a pattern can be scanned with a realistic tip, which will give us like this kind of a tip convolution problem, giving us erroneous information that is involving also the tip size too, which is actually related to this kind of an example where we get the tip information too, because the tips can be fat, right? And then we will have a problem, like you can see here, the fat tip problem. And So I will share my experience about how successful these have been in my courses and conclude with that. And as a last thing to remark, to give you last year's presentation again in MNTeSIG about lithography. This has now been published. An application on effective lithography training module that you can carry out with your students. I'll be briefly talking about that too. Thank you.